Awesome. So today we're going to learn together about power and electric circuits. And before we get into the whole mathematical equations and all the different properties of electric circuits, we're going to start off with a little history lesson about kind of where the terms come from and who came up with them and why they're named after these people and why a few of these people are really important. We're going to start off with James Watt. Okay, so power is measured in watts, and we'll write it all down later. But power is measured in watts, and James Watt was an entrepreneur and one of the fathers of the Industrial Revolution, and he helped to make improvements to the steam engine, and he patented it and basically got the term watt for power, for measuring the power, named after him. And that's significant because up until that point we had no real ability to measure energy over time. We had no ability to do that, but Watt gave us that capability. And we also need to pay a special tribute to Alessandro Volta. And Alessandro Volta, he is like the founder of the volt, the term the volt, and the unit of volts, or electric potential. And he's also the founder of the battery. And he made the first battery by using water and salt and then some metal strips that conducted electrical current through those metal strips. And with those two, we began to have a foundation of power and electric circuits. And so for power, we have power is equal to potential energy over time. Really simple. And potential energy is equal to the charge times the voltage over time as well, which is incredible because charge over time is what we call current. So we have power is equal to current times voltage. And power, like we said before, is measured in watts. And watts, right, potential energy is measured in joules. So watts is basically the measurement of joules per second, or energy per second, or energy over time. And that helps us to understand what these do together. Current and voltage produce energy through the movement of electrical charges through a circuit. And voltage is really simple, measured in volts, and current is measured in amps. And this equation is almost always going to be applicable in a circuit. You can literally always use this equation. And there's a few other equations that we can use in a circuit to find out what the power in a circuit is. But they're not always applicable. So there's power is equal to current times resistance squared. And that's really helpful, but it's not always applicable because we don't always have a resistor in a circuit. And we also have power is equal to voltage over resistance, and the voltage is squared in that equation. But it's not always applicable again because we don't always have a resistor. Like if we have some circuit, sometimes we have a light bulb, and that's it. We don't have a resistor in this circuit. Sometimes we do. Sometimes we can have a little resistor, but that's not always there. And so that's why this one is always applicable because you'll always have current and voltage to determine what your power is in the circuit. And so let's do a quick example. Just gonna erase part of that, and keep in mind kind of what we're gonna tie this back into, like, help us understand it in a real life concept. Let's try and find the power for this circuit, and we'll have this. Okay, and we'll say that and the voltage for this battery is going to be 20 volts. And we'll say that the current is equal to 10 amps. So then 20 times 10, awkward, 20 times 10 is going to equal 200. And that's going to be watts, right? So it's the entire power that comes back to this circuit, and it's in the circuit, is going to be 20 watts. And so let's kind of think about this, okay? So if we have a light bulb that is 20 watts versus 200 watts, we can kind of say that 200 watt light bulb is probably going to shine a little bit brighter because it has more energy going through it. And so watt is also, or power in an electric circuit, the power, the watts, the energy over time, is directly related to the intensity of brightness of a light bulb. And so sometimes you can overload a circuit with way too much power, and the capacity of a light bulb can't handle it because it'll be too small, and so then like the light bulb would break or burst. But typically that doesn't happen because of resistors in a circuit and whatnot. And let's do one more, and we can use one of these other equations that don't always work. Okay, and we'll say that the resistance is equal to 10 ohms, and the voltage is equal to 5 volts. Okay, so if we, in this one, right, we're going to want to use this equation right here, because this is the only one that has voltage and resistance. And so it'd be 5 squared, right, over 10. And so then we have only 2.5. I'm really bad at writing upside down. That's why I'm not a teacher. But we only have 2.5 watts. And that's why the most effective way to really measure is going to be this one, because there's no exponential decay or growth or increase or decrease with in power electric circuit with current and voltage. And yeah, there's your lesson. Obviously there's so much more, and there's more detail that we can really get into, but ultimately it's the flow of electrical charges and electrons moving through a circuit that causes differentiation in charges.